Strain aging damage mechanisms is a part of mechanical and metallurgical failure mechanisms. Description of strain aging damage mechanisms based on API 571. Strain aging is a form of damage found mostly in older vintage carbon steels and C0.5mo low alloy steels under the combined effects of deformation and aging at an intermediate temperature. This results in an increase in hardness and strength with a reduction in ductility and toughness. Strain aging damage refers to a specific type of deterioration that occurs in metals and alloys when they are subjected to mechanical stress and then allowed to age or rest at an elevated temperature. This phenomenon is particularly relevant in materials that have experienced significant plastic deformation, such as during processes like cold working or welding. There are some key characteristics of strain aging damage mechanisms. Number 1 is mechanism. The damage arises from the diffusion of solute atoms or often carbon or nitrogen to dislocations, the defects within the crystal structure of the metal, during the aging process. This leads to the formation of dislocation networks that can significantly increase the material's strength but also make it more susceptible to brittle failure. Number 2 is stages of strain aging that divided by 3 but not limited to following. The first is deformation. Initially, the metal is deformed, creating a high density of dislocations. The second is aging. When the deformed material is held at a specific temperature for a certain duration, solute atoms diffuse and interact with these dislocations. The third is strength increase and brittle phase. The interaction can lead to an increase in hardness and strength, but it can also result in reduced ductility and toughness, making the material more likely to fracture under applied loads. Number 3 of the key characteristics of strain aging damage is impact on material properties. While strain aging can enhance certain mechanical properties, it also poses risks in structural applications where ductility and toughness are critical. The embrittlement can lead to sudden and unexpected failures, especially in high-stress environments. Number 4 of the key characteristics of strain aging damage is applications and considerations. Understanding strain aging is vital in industries like aerospace, automotive, and construction, where structural integrity is paramount. Engineers must consider the conditions under which materials will be used to mitigate any potential adverse effects of strain aging. In summary, strain aging damage is a critical factor in material science and engineering, affecting the balance between strength and ductility in metals and influencing the design and safety of various applications. Affected materials of strain aging damage mechanisms based on API 571. Mostly older or pre-1980s carbon steels with a large grain size and C0.5mo low alloy steel. Strain aging is a damage mechanism that affects materials, particularly metals, due to the interaction of dislocations with solute atoms or impurities during plastic deformation and subsequent aging processes. The primary materials affected by strain aging include: Number 1 is low-carbon steels. Commonly used in construction and manufacturing, low-carbon steels are particularly susceptible to strain aging, which can lead to increased yield strength but reduced ductility. Number 2 of the primary materials affected by strain aging is high-strength low-alloy steels, HSLA. These steels can exhibit strain aging effects, influencing their mechanical properties under service conditions. Number 3 of the primary materials affected by strain aging is aluminum alloys. Certain aluminum alloys can experience strain aging, where the mechanical properties can change due to solute redistribution during prolonged deformation. Number 4 of the primary materials affected by strain aging is copper and copper alloys. Strain aging can also affect copper materials, particularly those undergoing cold working, leading to variations in strength and ductility. Number 5 of the primary materials affected by strain aging is titanium alloys. Some titanium alloys have been noted to undergo strain aging phenomena, particularly in applications where they are subjected to cyclic loading. Number 6 of the primary materials affected by strain aging is nickel alloys. Similar to titanium, certain nickel-based superalloys may experience strain aging under specific conditions and loads. Strain aging generally occurs at elevated temperatures and can influence the mechanical properties through mechanisms like increased yield strength and reduced ductility, making understanding this phenomenon critical for materials used in structural and mechanical applications. Strain aging critical factors. Strain aging is a type of damage mechanism that occurs in materials, particularly metals, due to the interaction of two types of stresses, tensile stress and time. The critical factors that contribute to strain aging damage are: Number 1 is tensile stress. Tensile stress is a primary driver of strain aging. When a material is subjected to tensile stress, the atoms or molecules are pulled apart, creating strain energy. Number 2 is time. The longer the material is under tensile stress, the more time there is for the strain energy to accumulate and lead to damage. Number 3 is temperature. Higher temperatures can accelerate the strain aging process by increasing the rate of atomic or molecular movement, allowing the strain energy to dissipate more quickly. Number 3 is temperature. Higher temperatures can accelerate the strain aging process by increasing the rate of atomic or molecular movement, allowing the strain energy to dissipate more quickly. Number 5 is grain size. The size and distribution of grains in a material can also influence its susceptibility to strain aging. Larger grains may be more prone to strain aging due to the increased likelihood of dislocation accumulation. Number 6 is dislocation density. Dislocations are line defects in the crystal structure of a material that can act as sites for strain energy accumulation. High dislocation densities can increase the likelihood of strain aging. Number 7 is stacking fault energy. The stacking fault energy of a material affects its ability to absorb strain energy. Materials with low stacking fault energy are more susceptible to strain aging. These factors interact with each other in complex ways, and their individual contributions to strain aging can vary depending on the specific material and loading conditions. Strain aging affected units or equipment based on API 571. Strain aging is most likely to occur in thick wall vessels manufactured from susceptible materials that have not been stress relieved. Strain aging is a type of damage mechanism associated with high-temperature exposure to metals. It is more specifically referred to as strain-induced precipitation or strain aging. The main effects of strain aging damage are seen on metals that contain small amounts of alloying elements like carbon, nitrogen, or phosphorus, and particularly when they have been cold-worked or have been subjected to repeated loading/unloading cycles. The affected units or equipment of strain aging damage include: Number 1 is welds. In high-temperature conditions, strain aging in welds can cause a reduction in toughness, which can eventually lead to cracking and failure. Number 2 is aircraft components. Strain aging affects the properties of high-strength, high-toughness alloys used in the aerospace industry, particularly in components such as wings, fuselage, and engine parts. Number 3 is power plants and nuclear reactors. Strain aging in high-temperature service can reduce the fatigue resistance of critical power plant components, leading to premature failure. Number 4 is pressure vessels and pipelines. Strain-induced precipitation can occur in high-strength steel pressure vessels and pipelines exposed to temperatures above 200 degrees Celsius, affecting their performance and reducing their lifespan. Number 5 is high-temperature furnaces and heat exchangers. Strain aging can lead to reduced mechanical properties and increased susceptibility to corrosion in high-temperature furnace components and heat exchangers. Number 6 is automotive and industrial components. Strain aging can be a concern in components such as gears, gearboxes, and other high-strength parts used in automotive and industrial applications. In general, any high-strength metal that is exposed to high temperatures and cyclic loading conditions may be susceptible to strain aging. Appearance or morphology of strain aging damage based on API 571. Strain aging can result in the formation of brittle cracks that are revealed through detailed metallurgical analyses, but damage most likely will not be identified as strain aging until fracture has already occurred. Strain aging is a phenomenon that occurs in metals and alloys, typically as a result of prolonged exposure to elevated temperatures or after plastic deformation. It involves the interaction between dislocations, defects in the crystal structure of the material, and interstitial solute atoms, such as carbon or nitrogen, in the material. It involves the interaction between dislocations, defects in the crystal structure of the material, and interstitial solute atoms, such as carbon or nitrogen, in the material. Appearance or morphology of strain aging damage mechanism. Number 1 is dislocation interstitial interactions. The primary feature of strain aging is the pinning of dislocations by interstitial solute atoms. As dislocations move through the crystal lattice during deformation, they can encounter interstitial atoms, which hinder their movement. This interaction leads to a higher density of dislocations and a complex arrangement of these defects. Number 2 is yield strength increase. Strain-aged materials typically show an increase in yield strength due to the increased difficulty of dislocation motion. This can result in a noticeable change in the stress-strain curve during mechanical testing, where the yield point becomes more pronounced. Number 3 is decreased ductility. While the strength of the material may increase, ductility often decreases. This can manifest as limited strain hardening, leading to premature fracture during tensile testing. Fractured surfaces may exhibit more brittle characteristics rather than ductile features. Number 4 is surface morphology changes. Surface examination of strain-aged materials may reveal signs of microstructural changes, such as the formation of small voids or precipitates that act as nucleation sites for fracture. These features can be observed using optical microscopy or scanning electron microscopy or SEM. Number 5 is fissuring and cracking. In advanced stages of strain aging or in critical loading conditions, small cracks or fissures may develop, typically initiated at grain boundaries or areas of high localized stress. Number 6 is microstructural features. In the microstructure, strain aging may be characterized by increased dislocation density, areas of localized deformation, and precipitation of secondary phases if the aging process effectively allows for precipitate formation. Number 7 is temperature effects. The morphology of strain aging damage may depend on the aging temperature. Higher temperatures can lead to more pronounced interstitial solute diffusion and related changes in dislocation behavior, while lower temperatures may result in more subtle interactions. In summary, the morphology associated with strain aging encompasses changes in dislocation structure, a corresponding increase in strength and reduction in ductility, as well as potentially visible microstructural features that indicate the presence of strain aging effects. Understanding these characteristics is crucial for evaluating the performance and reliability of materials subjected to mechanical stress, especially in engineering applications. Strain aging damage mechanisms prevention and mitigation. Prevention and mitigation strategies for strain aging damage include the following. Number 1 is proper material selection. Choose materials with high resistance to strain aging, such as high-strength, low-alloy, HSLA, steels or advanced high-strength steels, AHSS. Number 2 is control of temperature. Limit exposure to high temperatures, which accelerate strain aging. Ensure that the material is stored and processed at lower temperatures, especially during prolonged periods. Number 3 is reduce stress. Minimize applied stresses or load conditions that contribute to strain aging. This can be achieved through proper design, load carrying capacity, and stress levels. Number 4 is heat treatment. Implement heat treatment processes like annealing or normalizing to relieve stresses and improve the material's resistance to strain aging. Number 5 is mechanical working and forming. Reduce the mechanical working and forming operations to minimize the introduction of strain and subsequent strain aging. Number 6 is control of exposure to hydrogen. Hydrogen can exacerbate strain aging. Minimize exposure to hydrogen-rich environments or use protective coatings to prevent hydrogen absorption. Number 6 is control of exposure to hydrogen. Hydrogen can exacerbate strain aging. Minimize exposure to hydrogen-rich environments or use protective coatings to prevent hydrogen absorption. Number 8 is optimize production schedules. Manage production schedules to minimize material storage times and exposure to strain aging-inducing factors. Number 9 is implementation of advanced materials. Utilize advanced materials and manufacturing techniques that inherently possess better resistance to strain aging. And number 10 is research and development. Continuously update knowledge and understanding of strain aging, its mechanisms, and mitigation strategies to improve materials and manufacturing processes. Inspection and monitoring for strain aging damage mechanisms based on API 571. Inspection and monitoring are not used to control strain aging. Thank you.